My name is Xiaowei Yang. I'm from Duke University. I'm the session chair for this session, which I believe is the last technical session of SIGCOMM'. So our first speaker of this session is Ajay Mahimka. He's a lead inventive scientist at AT&T Labs in New Jersey, USA. His research interests span service quality management, application of machine learning and big data analytics to network operational problems and change management. He has published several research papers in top-tier conferences, such as SIGCOMM', NSDI, Connect IMC, and ICMP. So now please play the video. Thank you.
Hi, my name is Ajay Mahimkar. I'll be presenting our paper, A Composition Framework for Change Management. Service providers continuously deploy changes in their networks of the form of software upgrades, configuration changes, software patches, and technological updates, such as 5G. Change management consists of multiple phases. The first is a design phase, where one has to identify what type of change activity they would like to deploy in the network. This is followed by the planning phase, where one has to identify the best schedule for deploying the changes in a staggered fashion across multiple nodes in the network. In the execution phase, one has to carefully implement the changes on the individual nodes. And then finally, in the verification phase, one has to ensure the expected impacts of the changes are observed in the field. There have been several works on change management from academia as well as industry. Change management has been a long-standing problem for network operations. So what makes change management so hard? The first challenge is a very large scale in operational environments. So one has to deal with on the order of hundreds of thousands of nodes in typical operational environment. This is very challenging. Then there is heterogeneity. So one has to account for the different network functions, starting with routers, switches, servers, load balancers, and base stations, to name a few. With the introduction of virtualization and containerization, one has to carefully account for the cross-layer dependencies. So dependencies between the physical server, hypervisor, and the virtual function when it comes to coordinating these changes. Now, different network functions can have different vendors, which results in different implementations one has to account for when planning changes. Networks also continuously evolve, so the capabilities have to be able to keep up with that evolution. And finally, the topology. This can be very dynamic, especially with the virtualization and the continuous introduction or the decommissioning of the different types of network functions. So custom solutions where operations teams identify solutions for each type of network function, each vendor, or each change activity can be very daunting. Thus, the key challenge in change management today is to design solutions that are easy and quick to adapt with the network evolution. So we propose CoreNet, which is a dynamic composition framework for change management. So typically a change mob, which is a method of procedure, is a very large document that lists the instructions for implementing the change. So we modularize that procedure into reusable library of building blocks or Lego blocks. Right? Now by having these building blocks, one can bring this in to different types of change activities quite easily. This enables maximizing reuse. And we apply this concept across all phases of change management, starting with the design phase, wherein you take these building blocks and easily stitch or compose them into a change workflow. In change planning, you would look at different operation intents, which can differ across different types of activities, different network functions, and then take that intent and then automatically discover the best schedule for the deployment. And finally, in verification, one has to be able to account for different indicators of performance when you look at different types of change activities. So thus we design CoreNet to be highly dynamic and that can quickly adapt based on the operations intent. So as an example, let's take a change management workflow for deploying software upgrade. So you typically start with health check to make sure the instance is up and running. This is followed by traffic redirect. Right? So software upgrade, which can be sometimes disruptive to the service, you want to ensure that all live traffic is migrated away from that instance. And then you carry out the software upgrade. Once upgrade is completed, you would like to restore the traffic back. and then apply post check to check if the instance is taking the traffic and it's good. Right? Impact assessment is done to observe the performance behaviors. If you observe degradations, then you want to quickly roll it back. Now, given these different Lego blocks or building blocks, the challenge is now across different network functions or across different vendors, these Lego blocks today look very different. Right? So today there is a lack of standardization. As an example, traffic redirect would look different for routers, which use IP-based redirection, as compared to servers, which could use load balancer-based redirection. Now, even after we have the implementations, today we lack common abstractions for these building blocks. Right? Now, abstractions are very important when it comes to flexible design and orchestration into a workflow. So you should be able to easily plug and play into a workflow. Right? So now we address this in Fortinet by proposing a catalog, which is a library of building blocks. Now, some of the building blocks are NF agnostic, means they can support any network function by any vendor, right? Any change activity, right? This maximizes reuse. A good example of a NF agnostic building block is impact assessment, which is typically a machine learning capability or a statistical engine to analyze the impact. Now, once you create the time series, one can reuse the same building block across different functions. Right? So for such building blocks, we implement this once, get it right, and then maximize reuse. Now for NF specific building blocks, we create the abstraction and then support implementations across different types of network functions. Good example is traffic redirect. Now, given these building blocks, we propose a graph-based designer that will take these building blocks. Operations teams would be able to drag and drop themselves in a self-serve fashion and create their workflow by stitching them together. We use a BPMN-based implementation to support the designer. So an example here is a workflow for doing the software upgrade. So we have nodes, which are the building blocks, and then you have decision points, right, which determine the direction of the flow. Once you have the design, one would like to implement or orchestrate the change workflow. We use the Camunda-based orchestrator, and we add new capabilities to first automatically log the status of execution so that we know how much time a typical workflow takes when it comes to individual instances. Also, in case of failures, we would like to know which building block had a failure. So that logging is a very important capability for operations. Now, when it comes to alarms or failures, one has to be able to expose capabilities for manually interfacing with the workflow. So we have pause and resume, wherein after failures, a human or an operator can come in and then take some actions to fix that problem and then restore the execution of the workflow. After this, we come to planning, right? So the goal here is to identify the best schedule that conforms to operations constraints as well as minimizes the total deployment time. So there are multiple constraints that we came up with, right, that capture the operation intents. The first is the concurrency, which tells us how many maximum nodes one would like to support the change implementation on at a particular instance of time. Right? So an example here is EMS, right, which is the element management system, could have concurrent limits. Right? So what is the maximum number of nodes? Second is conflict constraint, right? So here you would want to account for any dependencies across nodes, even different network functions when it comes to planning upgrades. So this is to avoid concurrent upgrades, right? So a good example is the physical server and the hypervisor. Third is the consistency constraint where there are software dependencies, right, across nodes. So a good example is an LTE base station and a 5G node, which is co-located. So you would want to schedule the upgrades together to ensure software compatibilities. The fourth constraint is uniformity, wherein you have to deal with different time zones, right? So you would like to ensure that when an engineer is managing the upgrade a particular time, then the nodes belong to the same time zone. And finally, localize means no interleaving, right? So this simplifies the impact assessment, right? So you finish specific nodes and then move on to the next set of nodes. So given this operations intent, which can differ across different work groups and different services, we automatically generate the mathematical model or constraint templates. So no custom solutions, because having a custom solution for each composition can be quite onerous. So we then do dynamic on-the-fly generation of the model. meaning that an operator can come in, choose what constraints based on their intent, and then want to determine the best schedule, right? So we enable this through the dynamic model generation and then application of the optimization solver. In the paper, we have a solution that enables to deal with a large number of nodes on the order of tens of thousands of nodes. So I would encourage you all to look at the paper. Finally, coming to impact verification, wherein you want to support flexible rule composition, right? Because you may want to look at several metrics when analyzing the impact, different timescales, minutes, hours, or days, staggered rollouts, and external factors. So we propose a new robust time-aligned aggregate comparison. So as an example, let's take a study wherein you implement the change. Now you want to compare to control where you did not implement the change. Now this could be spread apart, right? Staggered, right? So what we first do is we time align them so that it gives you a normalized view of the impact, right? And then we aggregate them so that it enables easy interpretation of results for the operators. By doing this, we can now support a holistic view of the impact of the changes. So this works for any combination of the performance indicators. Now, we also share experiences with the use of Coronet in large operation environments. So we have Coronet for the design, planning, and orchestration, which was used for a limited purpose for SD-WAN and VPN software upgrades. We also share experiences with planning and verification of 7 million plus changes in LTE and 5G networks over last 3 years. Now, Coronet has been resulting in significant improvements in operational and change deployment efficiencies. So as an example, this graph shows the deployment time on the LTE node with and without Coronet. So with Coronet, we see a faster and efficient change rollout. So to conclude, we have Coronet, which is a new composition framework for change management, which enables significant code reuse and flexibility. We have learned several lessons over years. A very important one is composition, right, to deal with network evolution. This is a new capability, so buy-in from operations teams takes time, right? Also, data integrity has to be dealt with in operations environment. So we have to design solutions which account for data integrity and enables operations team to troubleshoot issues. In the future, we would like to look at high-level intent completeness and then push the bounds on end-to-end automation, wherein we can look at different phases and then enable users or operators to manage changes very effectively. With that, I thank you, and I would like to take any questions.
All right, so let's just check the Slack channel to see whether we get any question. Okay, so we have a question from Shi Han Lin. The question is, can Coronet handle self changes? If the self should be changed, how could such change be extended to a large scale?
A great question, and hopefully you can hear me now. So by self changes, probably you mean changes to the capability itself, right? Like for example, you want to update your optimization solver, or you want to bring in a new analytic for doing pre and post comparison. So yes, I mean, in a way, again, as we build software, I mean, we are trying to make it easy to plug and play, similar as we want to do it for the network changes, right? So as an example, say you want to bring in a new performance indicator. Say with LTE network, you want to look at end-to-end latency from the user perspective. And let's say now you have a new machine learning analytic that looks at, say, multiple G node Ds or relationships to E node Ds, right? So we build it in a way that we can easily integrate that, right? So I don't know the next comment about easy extension to a large scale, but yes, I mean, once you have that capability, then we can apply it to a large number of nodes in the network. So yeah, I mean, that's just the software design of Coronet across the different phases, right? But I think more importantly, definitely our goal is to handle new types of network functions, right? Like 5G coming into the network, you want to be able to reuse what you did for 4G from an operational perspective.
Thank you. Thank you. All right, so I actually have a question. So I just wonder, whether you can shed some light on if some like other networks they want to implement something like CoreNet, right? What is the development cost for CoreNet itself, right? So that's the one question, right? So the other question I'm also kind of interested in is like whether, what kind of changes CoreNet can handle, right? Like you mainly talk about the software update. How about, like, say, for instance, like configuration changes, right? And yeah.
Yeah, so definitely, I mean, that's a very good question. So, I mean, extension to other types of networks, say data center networks, or even across different service providers. So yes, I mean, some of the capabilities that we have designed, for example, analytics or the schedule optimization, right? Wherein, let's say in the data center networks, you might have different constraints for doing the scheduling, right? Obviously, you wouldn't upgrade, say, all the servers at the same time. So you would stagger them, right? Now, the question is, how do you handle conflicts, right? How do you deal with dependencies across server types? And so given the operational intent, if you can kind of formulate in a way that give it to CoreNet and it generates the mathematical model, then we can generate the schedule, the best schedule for deploying the changes, right? So in terms of extensibility, I mean, we have designed in a way that we can easily extend to new services, right? Now, when it comes, you also asked the question about development time, right? So I think where we are today, I mean, this has been over multiple years of development and experience and interaction with the operations teams. So definitely, if we had to build this again, I mean, there are some things that we probably would do differently. But yes, I mean, development time, I mean, it won't be, I mean, given that now we have some of the knowledge, I mean, probably we can re-implement it quickly. But if it's without knowledge, it will definitely take some time, right? Because there are so many layers, so many components from an operational perspective to deal with changes, deal with failures, and performance, right? Performance is another important aspect that you have to look at.
I see. Thank you so much. Okay, right. So if there's no more question, we can move on to the second paper of this session. Again, our speaker is Ajay. So please play the video. Well, thank you, Ajay, for a great talk.
Hi, my name is Ajay Mahimkar. I'll be presenting our paper Auric, which is a data-driven recommendation approach to automatically generate configuration cellular networks. There has been a massive explosion in applications that rely on cellular service. Applications such as first responders, emergency services, live streaming video, high definition, AR/VR, online stock trading, gaming, and Internet of Things. This has resulted in a significant rise in voice, video, and data traffic, due to which the cellular service providers continuously add carriers in their network to keep up with the increasing demand in traffic. Adding carriers results in increase in network capacity and coverage that in turn provides a very high quality of experience to the end users. Carrier addition comprises of two steps. The first is the installation of the hardware, wherein you create new carriers or radio channels on the base station. This is followed by software configuration in order to integrate the carrier into the network. Now, this process is expensive and time consuming. It is very important to accurately configure the newly added carriers. There are multiple functionalities in cellular services, such as traffic management, outage management, user mobility or handovers, and channel interference management. It is important to get these parameters correct in order to ensure high quality of experience. The state-of-the-art process in operations today is manual tuning, where you create these rule books guided by domain knowledge or operational experiences over years. Now, these rule books comprises of rules that guide the engineers to determine what the configuration parameter value should be for the newly added carriers. The challenge is to accurately acquire the rule books and maintain them over time, which are challenged by the continuous evolution of the networks through software upgrades or configuration changes. Right? There are several challenges that one has to account for when it comes to managing configuration on the carriers. The first one is the very large scale. One has to deal with on the order of thousands of parameters on the carriers. Second is high diversity, where different engineers across different locations may tune these parameters differently. As an example, a national park location could have different configuration values as compared to downtown locations. So using real world data, we observe that there is a very high diversity in the parameter values, which is captured using the distinct values. The third challenge is the complex interactions. As an example, when one has to tune the handover parameters, it is important to determine what the triggering conditions are, followed by the appropriate thresholds on signal quality. For example, RSRP, RSRQ. Finally, this configuration changes have a huge impact on service performance. So any misconfiguration can result in poor quality of experience and thus can defeat the original purpose of adding new carriers. We propose a new solution that we call as Auric, which is a data-driven approach for configuring new carriers. The idea here is to learn and recommend configuration from existing carriers in the operational network. The intuition is that similar carriers should have similar configuration. The idea is akin to content recommendation for new users. So as an example, one would first discover the similarity across users. Now for a new user, you don't have say browsing patterns, so you would look at attributes. So this problem for new users in machine learning is termed as the cold start problem. By identifying the similarity based on attributes, one can then recommend new movies or content to the new user. Analogously, we can do the same thing for configuring carriers in networks. The challenge here is, how do you identify carrier similarity? What are the attributes? How do you capture configuration dependency with these carrier attributes? Right? So we look at multiple attributes on the carriers, ranging from frequency, carrier type, whether it is serving first responder services or not, channel bandwidth, morphology such as urban, suburban, rural areas, so different locations in the network, cell sizes, and so on. So by discovering the dependency across attributes, we know which are the similar carriers, and using the similar carriers, we can recommend the configuration value for the newly added carrier. So here is the problem formulation, wherein we have carrier attributes, which are the predictor variables. So these are defined for all the carriers in the network, including the new carrier. The predictive variables are the configuration parameters that we have to identify for the newly added carrier. So we first learn the model between existing carriers for the predictor and the predictee. So C1 to Cn-1 are the existing carriers. Based on that model, we can then recommend the target values for the newly added carrier. So this formulation actually nicely presents us with applying supervised learning. In our case, we use classification to learn the model. Right? So the goal here is to learn the beta between the variables y and x. Right? Now there are several learning techniques that one can think of: decision tree, random forest, k-nearest neighbors, deep neural networks, which look at both linear as well as non-linear relationships, and finally collaborative filtering. Now one may ask the question, why don't simple techniques like cosine similarity work? This is because it doesn't account for the dependency between the attributes and the configuration parameters. So we then look at more sophisticated learning techniques. And we know that collaborative filtering will work well for our problem, right? So this is because of the high variability in the configuration parameter values, right? So the challenge in machine learning classically is how to deal with outliers and prevent overfitting at the same time. Right? So in our context, by observing the high diversity, we notice that certain parameters values, the distribution could be such that you have a lot of locations with the same values. So that means they are frequently occurring values. On the other hand, there are some values which are very rare, right? So those could be treated as outliers by the other techniques like random forest or deep neural networks. Right? So collaborative filtering is thus well suited to our problem and can learn these models accurately for both frequently as well as rarely occurring samples. Right? So let me illustrate with a simple example how collaborative filtering would work with chi-square test of independence between morphology, which is one of the attributes, and then configuration parameters. Right? So in this case, you have parameter P1 taking different values. So you first ask the question, are these two variables independent or not? Right? By applying this chi-square test of independence, we can discover if there is a dependency. Once we have discovered the dependent attributes, the next step is to identify similar carriers to this newly added carrier that have matching values. right? So as an example, if the new carrier is in an urban location, then we want to identify all similar carriers that serve urban locations. And then based on the matching carriers, we identify using a voting approach what the target parameter value should be. Right? So global learners is where we would take voting across the whole network. Right? So this is good because then you have enough sample points. But the challenge is that in order to recommend something in New York, Manhattan downtown, if you go all the way to California, San Francisco, maybe you might not have a good recommendation. So we propose local learners where we can scope the learning and then use voting from similar carriers which are in your geographical proximity, right? So for New York, we don't go all the way cross country, right? We would stick to New York, Manhattan, downtown, and then look for similar carriers. So that is the local learners. Using real world data, we observed that local learners result in a higher accuracy as compared to global learners. So we conduct evaluation using a very large scale data collected from an operational cellular service network. Right? So we look at 65 configuration parameters, which are things that we would like to recommend. We use around 400,000 plus carriers. So this is the whole network that we are looking at, and that result in 15 million plus sample points. Now this is a very good data set for conducting accuracy analysis. So we use a classic cross-validation approach to compare the accuracy of different learners, in this case, global learners. So as you can see here, other learners have an accuracy of around 90 to 92% versus collaborative filtering goes all the way up to 95%. So this is a good accuracy for prediction of the parameter values. So the graph here shows that the accuracy would vary with the diversity of parameters, right? So on the x-axis, you have configuration parameters with decreasing diversity, meaning the number of distinct values, and the accuracy goes up as the diversity goes down, right? So less the diversity, I mean, if you have less distinct values, it is easier to do the prediction, which is intuitive, and we validate this using real world data. Next, we observe that local learner, which applies the geographical proximity, actually outperforms global. Intuitively makes sense, and using real world empirical analysis, we validate that. Now, 96% with local learners is a good accuracy, right? However, 4% we had mismatches, meaning that whatever we recommend did not match the existing configuration. Right? So in this case, we asked the engineers to label the mismatch output. Right? And the outcome was in 28% of these mismatches, it resulted in a good recommendation, meaning that the engineers validated that these are good for the network. So we went and implemented those configuration changes. Now, 5% of them were actually resulting in an update to our learner. Right? In some cases, we had to incorporate missing attributes. In some other cases, we also improved our algorithm. Right? There were some ongoing smaller scale trials that actually indicated that these configuration recommendations may not be good for the network because one would want to watch the outcome of these trials. Finally, still a large fraction, so 67% of those mismatches were inconclusive because at that time, we did not have enough knowledge from an operational perspective whether they will result in an improvement or a degradation. Now, Auric has been deployed in operational setups and has been resulting in significant improvements to operational efficiency. So to conclude, Auric is a system for doing recommendation of configuration. Right? Lessons learned where trust and interpretation are very important for adoption. Because this is a new system and as we are rolling out across the network, simple explanation of the recommendation is important. In the future, we plan to explore at least two dimensions, which is the first one is to bootstrap configuration for the unobserved attributes. And second is to now bring in more information such as traffic and performance feedback to tune the configuration. With this, I thank you for your attention and would like to take any questions. Thank you.
Right. Let's check our Slack channel. We have a question from Sanjay. Really interesting work, Ajay. So this is a domain where accuracy may be critical given operational needs. but ML is intrinsically prone to inaccuracies. Is achieving 96% accuracy enough? And how do we deal with even a small number of errors, even if rare, that could have serious consequences? What are the consequences of getting errors? And any ways to add some validation in the future? Yeah, great question. Yeah, I actually have the same question. Yeah, so
that's a very, very good question, Sanjay. Yes, like you said, right? So I think the accuracy is a very big deal for operations. I mean, if you don't get it right, I mean, there are kind of severe implications, right? I mean, there is customer experience at the line, service performance. So if you get it wrong, I mean, it is a big problem, right? So actually, we went through a lot of trials across different parts of the network before really we can gain the confidence, right? So and the approach which is taking the recommendations from the neighbors, looking at similarity, made intuitive sense because that's how today engineers would configure them. Right? But where we stumbled upon was because if there are some recent trials going on, and then they would not want to push that recommendation because they are looking at the performance implication of the trial, and hence Auric recommendation was not good for them, right? So today, the way they would do it is, and it is semi-automated, right? Which is we are making the recommendation as part of launching the carriers, we would automatically deploy those changes. But once the changes are deployed, let's say they deploy the change yesterday, the engineers are going to watch performance, right? Is the traffic being load balanced between the old carriers and the new carriers? How is the performance experience? Throughput, latency, your call drops, are those all good? And really, when you're adding a new carrier, you want to ensure it is carrying live traffic, right? And there is enough traffic, there is enough load balancing. So today they do kind of semi-automated tests, right? They would look at the key performance indicators to make sure things are good, right? If there is a problem, right, that means after Auric recommendation was implemented, and if they're not satisfied, they would roll it back, right? Or they would, again, they would, based on their experience, or they would do a trial and error, right? They would make a change and then again observe for some time. So very good comment on automation of the validation or the verification. And this is something we are working on right now, which is once we implement the changes, I mean, we do have some automation, but then if the performance is not acceptable, then we potentially would roll it back, right? And these carriers come with the initial configuration. So far, I mean, we have not come across scenarios where it has resulted in a degradation, but if it does, definitely we want to automatically roll it back, right? So yes, machine learning inaccuracies definitely do matter. And so we are slowly rolling this out, slowly gaining confidence, and then putting in more automation from an operational perspective. Other thing is also performance, right? I mean, today we did not actually have performance in the recommendation. So this is another thing that we're looking in the future, which is can we bring in performance or traffic into the recommendation engine, where we can learn the patterns across your neighbors and see what configuration has given you good performance, right? And that will potentially increase the weight of that configuration, right? So, but performance is definitely key, and from the service perspective, we have to ensure performance is always good.
Thank you. So we have another question from Shihan Lin. Thanks for the talk. So Shihan is asking whether there's any related work that also uses machine learning for configurations, and how is Auric compared to them?
Yeah, so I think, I mean, in general, recommendation systems are there, right? In the machine learning community and for other services, I mean, take it music, take it content, video. I mean, people have been doing recommendation for a long time, right? So, and the idea is you look at what is common between this particular user and other users in the system, browsing patterns, your attributes, right? And then make recommendations. When it comes to networks, I have not come across, or maybe I have missed it, I have not seen where you look at automatic learning of this kind of relationships and then making recommendations, right? But in general, configuration anomaly detection, I mean, one can say that, look, there has been machine learning approaches, classic detections that have been applied in this context to identify misconfigurations, right? Because if I'm looking at the problem of multiple routers or multiple carriers, I can cross compare them, and we had a talk in the previous session, right, where we can look at dissimilarities and then flag as one as being problematic, right, or being unexpected, and then those differences could be used to flag things for the operators, and then they could make a decision which one is better, again, based on maybe they might do some trials, right? Or see if in the past, whenever they made a change, has that resulted in an improvement, right? But yes, so for configuration management, I think looking at a data-driven approach, I mean, from an operational perspective, would be something that I think in the future, as a community, I think we should, and from a service provider perspective, definitely that's an appealing direction.
Fantastic. I think we have just take one more question from Chen Yu Ying. He's asking, he said, thanks for the talk. And how does the model transfer to different carriers? Do they need to relearn the model? And the follow-up question is, are the data released? What could be done in academia? Yeah.
Very good question. I mean, the first question is easier to answer for me. So definitely, I mean, you have to relearn the model, right? I mean, even across locations in our network, just to give an example, say New York versus California, we have different models, right? Because the dependencies are different. And actually, we do much more fine-grained learning of the model, right? Downtown versus residential locations, the models are very different. User mobility, handover patterns are quite different. Density of the cells, density of the users, that all results in a different relationship between configuration. For example, your handover parameters or your tilt values or transmission powers are going to be different for different even locations, right? Now, if you go to different vendors, again, the model is going to be different, right? Again, because vendor implementations are different and the kind of parameters they expose are very different, right? So indeed different. And if you go across service providers, the high level policies could be different, right? So some operators might look at tuning throughput. Some other operators might look at tuning your call drop ratios, right? Again, based on your objective or intent, the way you configure the network could be different, right? 5G to 4G interactions, handovers, what's your policy? Now, based on that, again, different carriers or different service providers would have different policies and hence different relationships, and thus the models would be different. Now, second question is a harder one. Access of this data to academia, right? I mean, unfortunately, we cannot release some of this data because having kind of maybe that's a policy, but definitely we welcome collaborations. I mean, and we do have several across multiple universities. So if you're interested in this problem from a research perspective, a PhD perspective, or master's, definitely would encourage to kind of apply or talk to a few of us who are attending SIGCOMM, and that would be one way for you to enjoy the data and put together some interesting learning or analytic algorithms.
I see. Well, thank you so much. Thanks again for another nice talk. All right, so let's move on to our next paper. So the second half of this session is the papers are about network security. So our next speaker is Ayushi Arora. Ayushi is a second-year PhD student majoring in computer science and a research assistant under Dr. Christina Garman at Purdue University. Her research interests include cybersecurity, anonymous communication networks, information security, and applied cryptography. All right, so please play the video. Thank you.
Hi, my name is Arushi, and I'm a PhD student at Purdue University. I'm excited to share with you an architecture that aims to safely bring network function virtualization to Tor. For this work, I collaborated with Michael Rieninger, Dr. Stephen Herwig, Nicholas Francino, Jason Hurst, and Professor Dave Levin from University of Maryland, and Professor Christina Garman from Purdue University. Anonymous communication is necessary to ensure free, open communication on the internet, particularly in the regions of the world that suppress speech online, even for things like women's productive health or simply for differing political views. Strong anonymity, which means anonymity in the presence of a very powerful adversary, one that can view virtually all network links. Tor cannot achieve this. They explicitly assume any adversary can only view a small portion of the network. Other systems are able to achieve strong anonymity, but at the cost of higher bandwidth consumption or higher latency. It seems like this was the end of the story for anonymity, that you pick your point in the space based on which properties you want, and you are stuck with the system that gives you those properties. In this talk, I want to present a way forward that would allow us to assume different points in this space on a user by user basis, or even on a connection by connection basis. We start the system that has the best performance guarantees here, Tor, and introduce a new system we call Bento that lets users add functions into the Tor network itself, so that if they choose to do so, they can take on extra overheads to achieve stronger anonymity. And as I will show, they can do a lot more than that too. The outline of this talk is, first, I'm going to show you why adding network function virtualization to an anonymity network like Tor can be a good thing. I'm going to describe some specific applications that significantly benefit from being able to drop in arbitrary functions. Then I'm going to explain why it's a horrible idea to do this. I'm going to discuss various attacks on that this introduces. And finally, I'm going to introduce Bento, our architecture that makes this a good idea by making it safe to install functions on Tor relays. I want to mention that while I'm going to be presenting all of this in context of Tor, the Bento architecture is orthogonal to Tor, so we think our results apply to NFV more broadly. And as a result, we hope this work opens up a path to considering NFV in adversarial networks. We are going to be digging into Tor. Let's begin with a brief overview of how Tor operates. Tor is a peer-to-peer overlay routing system that aims to provide anonymity to users. There are typically three relays in a circuit: an entry node who communicates with the source, a middle node, and an exit node who communicates with the destination. The source node is responsible for choosing which Tor relays to include in a circuit and for constructing the circuit. Tor explicitly assumes that adversaries cannot view all communication on all networks. They assume that adversaries can be powerful, possibly even nation states, with control over their ISP's routing, but that no one can view everything everywhere. Although Tor is an extremely powerful anonymity system, it is not impervious to attacks. One of the most pernicious attacks that has challenged Tor for years is known as website fingerprinting attack. In a website fingerprinting attack, an adversary observes the traffic to and from a client. This adversary knows that the client is talking to someone, but does not know who that is. The idea behind the attack is that the adversary observes patterns of uploads and downloads. When the client sends a packet, the adversary cannot see what the actual contents of the messages were, but it can tell that something was sent. So the attacker records this. He continues doing this, monitoring both uploads and downloads. Prior to launching this attack, the adversary uses Tor himself to visit the website he expects the victim might try to visit, and he observes the patterns of uploads and downloads in his own traffic. This collection of patterns serves as a sort of database of website fingerprints. Many prior defenses have been proposed over the years, and they generally work by modifying Tor or modifying websites to introduce extra traffic so as to not match existing fingerprints. They have generally resulted in only minor improvements because there is still more fundamental problem here. The client herself has to be online and involved in the communication. This seems fundamental to communication. For a client to get a web page, they have to actively engage with the website, or do they? I will now describe how network function virtualization can provide a new path forward in solving this challenge. I am going to present the first Bento function, which we call browser. Bento is a system that Tor relays can choose to run. If they do, they allow users to install and run nearly arbitrary code on their relay. More on that later. All communications take place over Tor. So installing a function requires sending the function to the Bento server over a circuit. In this way, the Bento server learns nothing about the client it did not already know. This particular function operates as follows. First, it runs a web client locally on the Bento server. It uses this to download the web page Then it adds extra paddings up to some pre-configured amount. Finally, it sends the entire contents back to the circuit to the user. Bento function can be written in a high-level programming language. We use Python in our implementation, and in fact, a function like this is very easy. Here is the code for this function in its entirety. Let's consider what the traffic looks like during the website fingerprinting attack. The adversary sees two phases of traffic. When the user uploads and executes the function, and then later when the function delivers the contents back to the user. This looks the same for any website and renders website fingerprints useless. We evaluated this against the state-of-the-art website fingerprinting attacks that use deep learning, and we found that even a modest amount of padding renders these attacks ineffective. Browser is just one example of the wide range of functions that we describe in the paper. By this point, I hope that I have convinced you that being able to install functions on nodes in an anonymity network can come with benefits. Now let me show you why this could go so terribly wrong. The first set of threats have to do with an adversary installing functions. If an adversary can really run arbitrary code on another user's Tor relay, what's stopping them from storing illicit content on the disk, opening arbitrary network connections, snooping on other Tor traffic, leaking cryptographic keys? In other words, truly arbitrary functions could lead to arbitrarily bad attacks. Another set of threats arise when the adversary runs the Bento server itself. On one hand, such an attack could happen in Tor. It is designed under the assumption that peers can be adversarial, but in an NFV setting, this can be much, much worse. Such an adversary could alter the performance of the function, alter the contents of the data, leak cryptographic keys, and so on. In other words, how can we trust the network will truly run the functions we install? To quickly summarize, if we are going to add NFV to anonymity networks, we have to do it in a way that protects the network from the functions and that protects the functions from the network. Finally, I will discuss how Bento achieves programmable anonymity safely. To understand this, let's look more closely at what's inside a Bento server. We can think of Bento as consisting of three broad parts: providing an execution environment for user-supplied functions, a policy enforcement layer to exert some control over what functions can do, and the resources themselves that functions need to access. Our first goal is to protect the function from the server. Recall that the browser function downloaded web pages for a client and stored them on the Bento server. If we were to simply run a function like browser in the clear, the Bento server could see and possibly even modify the user's traffic. To prevent this, we assume that each Bento server is running on a machine that has a small trusted CPU like Intel SGX that is resistant to physical attacks. SGX lets you create trusted execution environments which allow you to run code on an untrusted machine while being certain that it is being executed faithfully. In particular, we make use of another system that co-authors on this paper developed called Conclaves. SGX itself is somewhat restricted in what it can run, but conclaves allow us to run arbitrary legacy code within a trusted execution environment. Every function can run inside its own conclave, protecting them from a malicious server, but also providing isolation between them, protecting functions from one another. This gets us part of the way there. But now we have the confidentiality and the integrity of the execution and memory of a function. But conclaves alone do not ensure the functions that are not accessing resources we do not want them to. This brings us the next problem: protecting the server from the function. Whenever a Bento function wants to access a system resource, the conclave forwards that request to our policy enforcement layer. The job of this layer is to ensure that functions cannot access resources the user does not want them to. So the first thing we need is for a user to tell us what resources they are and are not comfortable with giving up. There is already a concept like this in Tor in the form of exit node policy. This is a policy that users can specify to tell Tor what destination it is willing to connect to as an exit node. Some users decide to be an exit node for any destination, some for no destination, and many choose some middle ground. Bento strictly adheres to the exit node policy, and it is also introducing its own policy to allow users to express what resources they're comfortable in providing. We can call this middle node policy, and it includes things like what system calls it will support, how much disk space to allocate to a function, and so on. Bento servers make their policies public, and clients choose the Bento servers that provide what their functions need. Putting this all together, functions run in trusted execution environment and they forward all system calls to our policy enforcement layer, which decides whether or not to give them access to resources. To summarize, I have shown that making anonymity networks programmable can improve security and performance while also making it much easier to add new features. I've also introduced Bento, which makes programmable anonymity networks safe for functions and servers. We believe Bento to be more broadly applicable and that it opens up a path towards studying NFV and adversarial networks. To assist these future efforts, we've made our code publicly available here. Thank you for your time, and I look forward to your questions.
Thank you for such a nice talk. All right, so let's just look at our Slack channel. Let's see. So we have a question from Jeff Mogul. Next work, how does the average non-technical user obtain trustworthy NFVs to install into Bento?
Yes, that's a great question. So of course, if I'm getting it correct, you want to know about the overhead of running Bento within SGX. So of course, when it comes to SGX, there are some overheads that are of course there, but Bento design is not really tied to a specific TE architecture, and it just requires that one supports the properties needed by the TE. So, and even this is not a requirement of the Bento design per se. We can envision that there are some functions that do not require TE at all. And it just allows us to support a wide range of functions, as well as provide stronger security and privacy protections for both users and middle box operators.
I see. So the second question is from Payush Kumar Sharma. Thanks for the talk. It's an interesting idea. What do you think could be practical challenges in running Bento, given that it has additional requirements such as relay machines that have support of trusted execution environments such as SGX?
I think this is similar to the previous question that I answered. So Bento is not tied to a specific TEE. It's not tied to SGX. Well, of course, if we assumed, and this was our assumption that we were using SGX initially, but as I say in the talk as well, that we are open to using other TEEs as well. And also we use Conclaves, which offer the abstraction of containers of enclaves and thereby making it a straightforward to deploy multi-process scalable legacy applications within a dynamic number of enclaves. So yes, also there are some more functions that do not require TEEs at all. So yeah, we envision that there are a lot of functions that could be used without a TEE. And if we want to use a TEE, we assumed SGX, but of course, there could be other TEEs that we could end up using.
Okay, thanks. Yeah, so actually I missed the question, but I think maybe Arush, you can reply it in the Slack channel. So there's another last question, right? From Alan Zhaoxing Liu. Great work. Does Bento support multi-users to use SGX? And
Yes, of course. So yes, if as Bento server that has SGX installed or is using SGX, of course, there can be multiple users that can connect to the same Bento servers. And there are a lot of other security features that we talk about in the paper as well. And this allows multiple users to actually connect to a Bento server. For instance, we have containers that protect server operators from functions that maliciously overconsume resources. And then we also introduce sandboxing and resource accounting with our architecture. And we also have middle box stored policies. So yeah, of course, multiple users can definitely connect to Bento servers that utilize SGX.
Yeah, so the second half of the question is like how many users can deploy NF in a trusted machine? Like, do you roughly know, like?
So we haven't really gone into the scalability features of how scalable this would be in practice, but we performed all our experiments on Tor network itself with all the ethical considerations. And well, I think we tested with about 10 users or so, and then we got some good results. But of course, the scalability part is one of our future work that we are considering, how Bento servers, when they're deployed all over the network, how it would work over there. But of course, yeah, thank you for your question.
Great. Thank you. Thank you for the nice talk, and I'm so glad to see that you take the programmable network idea one step further into anonymity networks.
Thank you so much.
Sure. All right. So now let's move on to our last talk. So the speaker of the last speaker is Philip Gentner. He's a PhD student at the Technical University of Darmstadt and Fraunhofer SIT since 2019. His research is focused on DNS-based attacks against network applications, mostly finding new attack vectors and performing internet-wide studies, like in the paper he's going to present. He's currently aiming to be finishing his PhD in the end of this or start of next year and afterwards. And he'll be on job market looking for a postdoc position, preferably in Europe. All right, so let's start with the video. Thank you.
Hello and welcome to From IP to Transport and Beyond, cross-layer attacks against applications. I'm Philipp Geithner and I wrote this paper together with Tianxiang Dai, Haya Schumann and Michael Weidner from the German National Research Center from Applied Cybersecurity Athene, the Technical University of Darmstadt and the Fraunhofer Institute of Secure Information Technology, SIT. First, I want to give you a small overview over the following presentation. First, we will look at DNS cache poisoning, the history, how it is applied, and what are the methodologies to do it. Then we will look at how to apply DNS cache poisoning against applications. I'll present you our internet measurements, i.e. how many internet systems are vulnerable to the different cache poisoning methodologies. And in the end, we will look at countermeasures and conclusions. So what is DNS cache poisoning? Generally speaking, DNS cache poisoning is the injection of malicious DNS records into a DNS cache. This can be done via different methodologies. The first and easiest methodology is to brute force the transaction identifier. There were then countermeasures to counter this attack, essentially to add the source port randomization, to add some more randomness into the DNS response, which have to be matched.
And after this countermeasure has been added, there were more sophisticated attacks like copying the challenge response parameters completely from the benign packet from the name server via fragmentation, or to infer the source port, the randomized source port, via an ICMP side channel. And the first question for our research paper is, which methodology is the more effective one in which scenario? The second question is, since DNS cache poisoning has been used and analyzed mostly to redirect HTTP traffic, but many more applications use DNS, the question is how to attack other applications except HTTP to exploit applications, essentially. So how to exploit cache poisoning against different applications? First, we want to emphasize that not all applications are equal. So to exploit an application using cache poisoning, you have to look at the use case in which the DNS is used. And we find 3 different use cases for DNS in typical applications. The first use case is location. For example, in HTTP, the client uses the DNS to find the IP address of a server which is specified by a host name. The second use case is federation. For example, in mail, a mail server finds the mail server which is responsible for a domain by looking up the MX record for this domain and finding the host name of the mail server. And the third use case is authorization. For example, in SPF, which is also an application of mail, the domain owner can specify mail servers which are authorized to send mail coming from this domain. Furthermore, for example, cloud services use the DNS to validate the ownership of a domain. And this is also used in domain validation for CAs, for example, where you have to put a token into the DNS and then the CA knows that you are the owner of the domain. The second important property of an application when exploiting it via DNS cache poisoning is how to trigger a query with the application. We do a taxonomy of different query triggering methods in applications and find some important properties for query triggering. The first important property is the control over the query, which is needed to trigger a meaningful traffic volume. Essentially, what this means is that if you cannot set the query, or if you cannot set the domain where the query goes to, you can only trigger queries to the same domain again, which won't trigger a meaningful amount of traffic simply because the query will be, or the record will be cached, and so only the first query will actually be sent to the name server. This is important for probabilistic methodologies, for example, the SAT-DNS attack, which is the port inference methodology, or the fragmentation attack, because these methodologies are probabilistic, and so the cache poisoning doesn't actually always work. And the second important property is the timing predictability to improve the success rate. Essentially, for example, for the fragmentation attack, you need to predict the IP ID of the name server response, and this can only be done if you can predict the timing precisely. And even for methodologies which aren't that timing sensitive, it is good to predict the timing somehow because, for example, in a BGP hijack, you can release the BGP hijack earlier if you know when the query arrives. The second thing when looking at how to trigger a query is that we found that actually in many cases you don't actually have to trigger a query with a resolver using the application you want to attack. For example, we found that 79% of the web client's resolvers can be triggered with an open forwarder which forwards to the same resolver. And there are other third-party systems like SMTP which can also be abused to trigger a query. Finally, when looking at applications, we look at the possible attack impact. Essentially, what happens if the DNS cache poisoning is successful. And we divide this in 3 different attacks. The first attack type is the hijacking, essentially meaning that the attacker hijacks the connection so the connection doesn't go to the legitimate target but to the attacker. This then can be abused for eavesdropping, for example in email, HTTP, XMPP, etc., or also to do majority attacks against systems which use essentially results from different servers, for example NTP and also cryptocurrencies. The second attack type is the downgrade attack, where in security mechanisms, some security mechanisms actually decide to not employ a security policy if the DNS fails. For example, in case of SPF, because the security policy is actually stored inside the DNS, so without DNS working, you can't apply it. And the third attack impact is denial of service, where you can simply cause the application to have no connectivity with the target service. After having looked at how to exploit DNS cache poisoning against different applications, we now looked at how many internet systems are vulnerable to these attacks. We compare 3 different cache poisoning methodologies and look at if they apply against different resolvers from different datasets, which apply to the applications we analyzed in the previous segment. We compare BGP subprefix hijacks, ZDNS-based port inference attacks, and fragmentation-based copying of the challenge response parameters from a benign fragment. Our results show that the ZDNS attack only applies against a few resolvers, since most resolvers were patched after the attack has been published earlier last year. Our results also show that the fragmentation actually applies against many resolvers in some datasets, but in other datasets they don't apply against any resolvers. Essentially, we can say that there are no active countermeasures at most resolvers, except in some cases, for example, that the Google public resolvers filter fragments incoming to their resolvers, and also that many certification authorities do this to counter an attack which has been published earlier. Finally, we also look at subprefix hijacks, which essentially only depend on the network size or the size of the BGP announcement, and thus there is no countermeasure in this case, and just depends on how big the network is, essentially where the resolver is in. We also apply the same methodology to infer the vulnerability of domains against the same cache poisoning methodologies. In our comparison, again, the ZDNS attack only applies to a few name servers, since most name servers do not apply rate limiting, and thus the ZDNS attack does not apply to them. We also show that fragmentation only applies against few name servers as well, since the domain needs to have or the DNS responses from the domain need to have a certain size to be fragmented at all, because name servers typically employ a minimum MTU under which the fragment isn't fragmented even if you send a packet too big message which says so. And finally, we also show that subprefix hijacks again apply to most domains, and since again it only depends on the network size of the network which is attacked. As we have shown, there are still many internet systems vulnerable to DNS cache poisoning attacks. We now look at countermeasures to prevent these attacks. Essentially, there are 2 types of complete countermeasures. The first is to deploy DNSSEC, which enforces full authentication of DNS records and therefore blocks the attack. The second is to use third-party authentication methods, for example TLS, which authenticates the remote server so the authenticity of the DNS response isn't required anymore by the application. However, we want to emphasize that third-party authentication does not work in all DNS use cases, because as we've shown, some security mechanisms like SPF and RPKI are designed to not apply a security policy when the DNS becomes unavailable, and this can be achieved even with cache poisoning, even when DNSSEC is enforced at the resolver. Finally, we also list countermeasures against individual cache poisoning methodologies. For example, blocking fragments and DNS resolvers or applying RPKI to prevent BGP hijacks. Finally, we come to our conclusions. In this work, we showed that cache poisoning endangers more applications than previously known. We also showed that depending on the methodology, large parts of the internet are vulnerable to DNS cache poisoning attacks. And finally, we showed that DNSSEC deployment is critical to prevent cache poisoning attacks at a conceptual level, because otherwise network operators have to deploy countermeasures against each cache poisoning methodology individually. Finally, we want to thank you all for your time and interest in our presentation and wish you a pleasant day. Goodbye.
Thank you, Philip.
Hi.
So, yeah, okay, we have a question from Shi Hanlin. Thanks for the talk. Is it possible that employ DNS cache poisoning to compromise TLS connection?
Not directly. So the point, I mean, of course, the point of TLS is to prevent against man-in-the-middle attacks, and essentially by DNS cache poisoning, you become a man-in-the-middle. However, there are some properties of, so there are some things you can attack. So for example, if you have a, so you don't use TLS for using TLS, you use an application. And you might be able to attack this application even when it uses TLS, for example, because obviously if you do DNS cache poisoning and just provide an IP address which points to somewhere and there's no service there, you are essentially doing a denial of service attack, and TLS can't protect against that. And then it depends on the application how it handles a maliciously inducted connection failure. For example, we showed in actually, this is a bit ongoing work, but we showed that in RPKI, you can essentially make RPKI don't check something, because if it can't do a connection for over a day, it will just don't check the security properties. And then it doesn't matter if you use TLS or not, because it's just like, it's a fallback if something doesn't work. And the other point of where TLS is kind of vulnerable is that TLS essentially needs revocation. So if you use CR, how are you called? Certification revocation lists or OCSP, both of them are based on that the client needs to do a connection to somewhere to check the validity of the certificate. And if you essentially break this connection so the client can't check it, then the client has again decide if he falls back to less security or if he blocks the connection. And yeah, that's then, it's a protocol design decision essentially if it's vulnerable or not. But yeah, essentially it comes down to you can induce denial of service, and what does the application do if you can do that.
I see. Thank you. So there's a follow-up question asking whether DNS over HTTPS or DNSSEC are better solution. Right?
So against these attacks, DNSSEC is the better solution simply because DNS over HTTPS only protects the link between what is essentially the client, so you have the web browser, for example, and the recursive resolver. But the link between the recursive resolver and the name service isn't protected by DNS over HTTPS. That's just not how it is designed. DNS over HTTPS is, you could use it, but there's no standard for it. It's only meant to protect the link between the client and the resolver, not between the resolver and the name server. And actually, most of these attacks are done between the resolver and the name server, because that's the link you see in the internet. You can't really know what, I mean, yeah, there are ways, but typically, at least the methodologies we looked at, they actually, even if you use DOH, the DOH is just not used on the link we are attacking. So that's why I would say DNSSEC is the better solution. But then again, obviously, DNSSEC has other problems. So it just depends on which attack you're doing. So generally, I can't answer that question.
All right. Thank you. Thank you for the nice talk. And
yeah, thanks for the questions.
Yeah. Okay. I think that's all. This concludes our session.